Hi there. My name is Preston Smalley. This is going to be my term project presentation for my planetary systems class instructed by Dr. Adam Kraus. Today I'd like to talk to you a little bit about exoplanetary atmospheres, where the field of study has been and where it's going in the future. So this is a synopsis or summary on the annual review posted by the Department of Astronomy and Astrophysics. There's the link if you'd like to read it. It was published in 2019, August of 2019. So first, we're going to do a little bit of background. Why do we want to study planetary atmospheres, right? So I'd like to make the argument that they are important for discovering and examining planetary processes. They are Rosetta Stones, if you will. They help answer some questions such as, how did the planet evolve? What is the atmosphere made of? Is it similar to the planets we are familiar with in our solar system? We will find that often they are not, in fact. And lastly, is it hospitable for life? This is a question a lot of people want to know. Is there extraterrestrial life out there? And studying planetary atmospheres is assisting with that currently. So the field began as a whole within our own solar system, classifying the planets as you would imagine. We found that there are gas giants, ice giants, and terrestrial planets. Overall, pretty boring. Just 3 classifications based on mass and size. But we soon found out that the universe is much larger and more diverse than our own solar system would lead us to imagine. So that brings us to some early discoveries. Around the turn of the 21st century, there was a thing you probably heard of known as the Hubble Space Telescope, and it assisted in finding some exoplanets, even though that wasn't its original purpose. Fewer than 25 exoplanets were actually known at this time. If we compare that to over 100 that we know of now, that's less than a fourth. Exoplanetary research was difficult at this time. It required really high precision machinery that wasn't really around, really good telescopes that we didn't have. As I said earlier, Hubble Space Telescope was not specifically designed for studying exoplanets. And for these reasons, early results were highly debated for their accuracy. It's worth noting that the early data analysis methods at this time were not up to par, and many papers found themselves revising themselves over and over again. But over the years, these analysis and data recovery techniques continued to improve. Fast forward to now, where detections of new exoplanets are made on a daily basis. And it's unprecedented with unprecedented precision. One of the technological advancements that helped a lot with this was the development of the Wide Field Camera 3, will be referred to as WFC3, on the Hubble Space Telescope, which helped primarily with the near-infrared wavelengths, although it did do some work in the optical region as well. Space Telescope imaging spectrograph also was a technological advancement later on that helped make advancements in the optical and ultraviolet wavelengths. So let's talk about some methods that were used to obtain these results we're going to talk about today. Coincidentally, or not so coincidentally, the methods used in modern day exoplanetary research are the same that we talked about in class with our instructor, Dr. Kraus. These are transit spectroscopy, high resolution Doppler spectroscopy, also known as the radial velocity method from class, and direct imaging. Each method is great in its own respects, but today we're going to be focusing mainly on transit spectroscopy because it was arguably the most successful and still is to this day. To this day, it has helped discover atmospheres for over 100 exoplanets, and over 20 of these were observed in different bands, in different wavelength bands. I mean, so as I just discussed on the different telescopes. They are used for different bands of wavelengths, like the infrared or the ultraviolet or the optical. So let's do a little review on transit spectroscopy. I don't want to spend too much time with this because I'm sure you've heard of it. So when the planet passes in front of its host star, you see a dip in brightness as a function of time. We all know this. Cool. But how does this help with exoplanetary atmospheres? How does it help our study? So you may remember from your early physics classes that when an atom or molecule undergoes a energy transition, it absorbs or emits a wavelength of light, a characteristic wavelength of light that is specific to that structure of that atom or molecule. So you see here some incoming starlight, right? This is from the star that's behind the planet, right? This planet looks like Earth, most don't. But blue, look at this blue wavelength, right? It gets kind of cut out. So it gets absorbed in the atmosphere, right? So we know that some atom or molecule absorbed this wavelength of light that we should be seeing, but we're not. And if we isolate that wavelength, we can tell where it should have come from, what should be there, but it's not, right? That may be a little confusing. But a wavelength is associated with a characteristic atom or molecule. If it's not there, and we know the wavelength should be, then we know that atom or molecule is in the atmosphere. Okay, so now that we've talked about transit spectroscopy, let's dive a little bit deeper into the three kind of configurations that transit spectroscopy is used in modern times. You can go transmission spectrum, emission spectrum, or the phase curve spectrum. We will spend the most time on the transmission spectrum, which is what we just talked about in the last slide. I'll show you the absorption spectrum right here. This is when the planet passes in front of the host star. This is called a primary eclipse. This is where absorption features are imprinted on the stellar spectrum. We have the emission spectrum, where this is measured when the planet passes behind the host star. This is called a secondary eclipse. Both planetary spectrum and stellar spectrum are observed simultaneously just prior to the secondary eclipse. When the stellar spectrum is subtracted off from this combined spectrum, we get the planetary spectrum, which is what we want. And lastly, very quickly, we'll talk about the phase curve spectrum. These are functions of wavelength. If we want to know, well, what does the planetary atmosphere look like when it's at this point in its orbit, or when it's at this point, when it's at periastron, or something like that, right? We can look at the phase curve spectrum. This is a planetary spectrum as a function of orbital phase. So what are the purpose of these? Transmission is basically helping to measure the thickness of the atmosphere as a function of wavelength. And this sets constraints on atmospheric constituents and abundances, which we will talk about in just a few minutes in the results section. This is what we're going to be using today. But just so you know, just for a little bit of background knowledge, emission spectrum is mainly used in temperature discussions. And the phase curve, like I said, measures as a function of phase, of where the planet is in its relation to the host star. So results, what are the results? So we're going to talk about chemical compositions of exoplanets, of their atmospheres specifically. I'm going to start talking about atomic and ionic compositions. We will continue on to talk about molecular, and then we'll talk about how much of these things is there in the atmosphere. How abundant are they? So nearly 20 chemical species have been discovered in the atmospheres of exoplanets. Sodium and potassium are among these. They were discovered in transiting hot Jupiters using the Hubble Space Telescope in the visible range, which, and if you want to know those characteristic wavelengths, there they are. Helium was detected in a giant exoplanet as well. And we had our first potential inference of lithium in an exoplanetary atmosphere around 2018. So for molecular advancements or detections, we can thank the Wide Field Camera for its advancements in the near infrared. This helped to detect water, the big H2O, methane, and ammonia, all in exoplanets, which is miraculous. We noticed those in our own solar system. So some similarities, some differences. Water has been detected with high confidence in the atmospheres of over 10 transiting exoplanets. And we really want to hone in on water here because it was, it's the easiest. In fact, you'll see here, we know water has a feature, an absorption feature near 1.4 micrometers. The wide field camera spans the 1.1 to 1.7 micrometer band. And so this helped us find those 10 transiting hot Jupiters, which contain water in their atmospheres. Here is a picture of the data for those that are interested. You can look at the paper itself for more info here. I'm not going to go into too much detail because of time constraints. But the main gist here is that look how all of these H2O abundances are subsolar. That's what the theory predicts. Also interesting to note that many of these were done during the secondary eclipse of the planet. So here a little quote I thought was very nice from the author of the review. He says, overall atmospheric characterization is a revolutionary development in the exoplanetary field. This is something I really want to drive home to anyone watching. This is a new field. It's a booming field, in fact. A field that wasn't around 2 decades ago. So yeah, very cool stuff. Very cool times that we live in. Finally, I want to move on to some of my thoughts and my conclusions. This is more of an editorial, if you will. So we have, it's clear that the modern technological advancements that we just discussed, such as the wide field camera in observational facilities and theoretical modeling, have led to successful creation of a large range of constraints for atmospheric properties of giant exoplanets. We have many high fidelity detections been made, means many very accurate detections being made. As we just talked about, atoms of ions of sodium, potassium, and helium, as well as molecules of water, methane, and ammonia. There are others listed. I just didn't go into them in the review. If you'd like, the link is at the beginning of the PowerPoint. The astronomers hold great confidence in these abundance constraints for H2O, partly because of that strong feature that I talked about, but also because of these theoretical modeling advancements that have been made that are really great. I agree with them. I think they're astounding, and I really like where the field is going. So, issues, right? Issues are few and far between. Excuse me. Partly because it's a review of the most crucial developments we've made in the recent years, so it's got to be accurate, right? Right? Well, maybe not so much. It is great, but it's important to remember that the transit method is a constraining method. It's not so much going to give us exact values. We don't know exactly how abundant water is in these things, but we do know some constraining values. It gives us an idea of a ballpark, if you will. Also, an issue with the transit method is in the signal to noise ratio, not as high as direct imaging, for example. So I want to talk a little bit about what I talked about on the previous slide. Let's see if I can go back. Sorry. This theoretical modeling. Very important. The review talks a lot about it. I couldn't go into much detail with it. However, I do cite in my paper their previous year's review, which does go into great detail on this. So some questions you got to ask when you come across this. Is it believable? Are we cutting out some crucial data on accident? When we're cutting out this noise, are we leaving out data? I think it's unlikely, but I do think it's possible. And I would like to see a bit more discussion on that and why it's okay to take these steps that we do in cutting out data. All right, so where do we go from here? Well, there's a new thing. I don't know if you've heard of it. Probably have. It's called the James Webb Space Telescope. It's the new big thing in the space technology era. It offers unprecedented precision. Sounds like an ad almost. I swear I'm not affiliated with James Webb or Space Telescope. It's got a large aperture, high sensitivity, and a wide spectral range. So that means it covers a lot of wavelengths, especially in infrared. There are some studies that investigate where this could lead and how this could help us. So if you're interested, they're listed here on the PowerPoint, as well as in my paper. So some final words. The field is growing at a tremendous pace. Just a decade ago, as I said, only a handful of exoplanets have been discovered, and we are now approaching on the order of hundreds of exoplanets that are being surveyed, classified, and examined. I should say exoplanetary atmospheres, because we know of thousands of exoplanets nowadays. And I'll leave you with this. This is a quote by the author. I think it's great, and I think it's great to end on. These advancements, driven by both current and upcoming facilities, the study of exoplanetary atmospheres is entering its golden era. So go out there and study some exoplanetary atmospheres. And who knows, you might find the next Earth. Thanks. Have a good day.